Testing. Yeah, I can. I'm testing my own mic. Okay. Yeah. So I will be looking at. Hang on. Let me just take a look at. I will be looking at some of the questions you posted. Okay. This one. Starting with this, is it? Okay. All right. Yeah. Let me just get my thing started. Okay. Which one are you asking for? Part D. So part C, you're okay. Okay. So this is a 2025 RV paper, huh? 2025 RV. Yeah, I kind of will need a bit more context as well, cause yeah, cause I need to see what's the original graph here. Do you have the file? Should be quite easy to find. But okay. I mean, what's the other question? So, which is the next one? Okay. Are you talking about this one? Just the last part? Okay. So I would say that your first part, if anything, I would also suggest. I know you're using a soft copy. If anything, I would still suggest that you use blue. Because sometimes it's not easy to see your own answers. It's not me. I mean, I can read, right? Obviously, but I think it's like, uh, you know, when you're starting out and all that, I think it's better to use blue ink because sometimes you might not. I think you might not be able to tell. Um. Oh, why is this blue? So this part is here is wrong. Yeah, that part is wrong. So it's not constructive interference. So for stationary waves, basically it's a continuous series of constructive and destructive interference. Even if you know it's wrong, then I would also suggest that you do the corrections as well. Uh, yeah. Sure. So it's like an extra convoluted question. It's like, so you had a point source at first, right? And then you have a wall. And then for the first scenario, the wave is traveling perpendicularly like this, right? Over to the wall, and then it bounces off, right? Is that right? Then you get your standing wave, right? Yeah? No, 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 no. Wait, what are you talking about? Are you talking about you didn't interpret this as an intensity question? No, no, no. I mean, I'm not done yet. As in, like, you know, um. So then they're saying that, are they saying that, then when the standing wave forms, because I mean, this is the first time I'm reading the question, right? This is like, yeah. So we have, how many nodes did they say there was? They said there was, they said there was two other nodes, right? What was the previous case? Yeah, because I think it's all linked, right? So yeah, there are only two more nodes between the source and the wall. Okay. So the wall will be a node as well, right? Yeah. So the wall is also a node. It's also a node. And this is a node. Okay. And then it says there's two other nodes inside, in between. Right. So I'm assuming that the wave kind of looks like this. That's the standing wave lah, at first, right? That's the first one. Then they're saying that there is a position X. This this is like very, position X is right here. Yeah, position X right there. And then they're saying that there is a what when the sound wave travels directly from point source to the source is replaced with a point source that emits sound uniformly in all directions. Don't know how that makes a difference, but okay. So now you have something that looks like this. Yeah. And then they're saying that once it's at location X, it has an amplitude of 3.0 times 10. So the amplitude, right, is 3 times 10 to the power minus 5. Correct? 3 times 10 to the power minus 5, that's amplitude. That's what they say, right? The location of the node nearest but not at the source is marked as X. I'm just following instructions, sorry. What, is that right? No, so this part here is no longer a standing wave. Yeah, yeah. So yeah, so it's a bit odd. I mean it's a bit convoluted. It's like why don't they just say it directly? Good night, right? Good night. Okay. Oh yeah, seeing you guys. Coming home early and seeing you guys. Okay. Uh so yeah, I mean it took me a while, right? It's like when I was reading the question, I was like, trying to process it in my head. Then I realized that, oh, so firstly, there's a position next to the source, which was the node and is position X. Then they say that the sound wave, when it travels to this point X, I mean, I'm just reading the question and I'm taking it literally. And it says that the sound wave, when it travels to X, it has this amplitude, right? So it has this amplitude. And then they're saying calculate the amplitude of the wave, calculate the amplitude of the wave, right? After it has been reflected by the wall, and then it travels back to location X. So, it's super convoluted. So it's like, oh, the wave will now pass by X, hit the wall, and then travel back, right? So you're not wrong to say that the note should have no no amplitude, right? Yeah, because that's what we imagine notes to be. However, you must also remember that that's in a very ideal situation. Like, standing waves, right? We say a note is a note. That means there's no displacement, and then we tell ourselves that, oh, but that's the definition of the note, right? Like there's no displacement. But that's an extremely ideal situation because we're assuming that the incident wave and the reflected wave, right, they perfectly have the same amplitude at every point. Then they will cancel out very nicely at the nodes, right? Yeah, I mean that's what it's supposed to be. I'm guessing what's happening here, D part one, and then maybe on later on D part two, they will probably ask you something along the lines of like, why is the node not completely uh zero displacement? And I think it has something to do with this. So what they're trying to do is they're trying to get you to they're trying to lead you on to that point whereby you see the sound wave goes here first. I mean, why does nodes have no displacement in the first place? Because the incident wave has a certain amplitude, the reflected wave has a certain amplitude, and they meet at that point and they completely cancel out, and it has the same amplitude, assuming, right? Ideal situations, they cancel each other out like that, you know, like this. They, cancel nicely flat note right there. Okay, right? I suspect this is what's gonna happen. They're gonna ask you to suggest why the node is not completely zero, but it's okay. We'll wait for that later. So this question here, right? These 3 marks here, like it's a bit strange as well. It's simply just us trying to calculate the amplitude of the wave once it's come back. So I suspect what they're trying to say is that oh, when it's going towards its large amplitude, when it's coming back, it's not so large amplitude. Like, yeah, I think that's what they're. But that's later. So now I'm just, basically we just need to figure out how far has this wave traveled for from this point to the wall and back again, and then we use an equation to figure out what's the new amplitude of a wave. So we probably have to recognize that amplitude of a wave for a point source, right? For a point source, amplitude is proportional to 1 over r. Yeah, are you aware of this? Are you aware that it came from this relationship? Intensity is inversely proportional to r squared. Intensity is proportional to amplitude squared. Now this is for 3D point source. All right, 3D point source like this. Okay, so I mean, frankly speaking, honestly speaking, I think the idea, I mean, the actual equation for this will be intensity equals to power over 4 pi r squared, right? So intensity is 4 pi r squared, like that. Yeah. So amplitude is 1 over r. So I guess in a way the question is basically asking you like, you know, when you are, I mean, how far is it from the source? Like in terms of like distance, how far is point X away from the source? Half. No, no, no. From X, from the source X. Yeah, yeah, half a wavelength, right? Okay. Then, like when it comes back to X again, what's the total distance traveled? 2.5, right? So 2.5. So half and then 1 and 2. So 2.5 wavelengths, right? And yeah, that's what they want you to do. When you're half a wavelength away, the amplitude is 3 times 10 to the power 5 minus 5 meters. So what happens when you're 2.5 wavelengths away? Like what would be the new amplitude? No, no. Our Yeah, the wavelength. So one is half wavelength. So okay. So that it's proportional. So what we can do is like like most people don't like to do, yeah, most people don't like to do ratio. So what you can do is you can just put k. You just put k, right? This really? Okay. I mean, to me it's fine, right? I mean, to me, you just need to put k as a subject, right? R times amplitude, right? So the distance, right? So the first one was half a wavelength. But what's a wavelength though? Which is how much? Sorry, it was not shown. That's why it's 3 mark. Oh, is it here? Is that your lambda? 15 cm? Okay. Oh, what? 15 divided by 5 divided by 4. That's wavelength. Okay. Okay. Which is 12. So the first distance is 6. 6 times amplitude. Place what? Sorry, why are you placing what? No, no, the source is taken as a node. That's what I saw in the previous part, right? They say that the source can be considered as a node down here. Yeah, yeah, I know. What I'm saying is that the source can be considered as a node. There are 2 more nodes between the source and the wall. I don't know why you put anti-node though. Yeah, it should be a node. No, no, that's the point. So that's why down here I said node, right? So the location of the node nearest, but not at the source. That means we're not talking about the node at the source. We're talking about the node nearest to the source, which is this one here. Yeah, yeah, yeah. So what was it again? Yeah, so this one here. So then we find out what's the second amplitude. Amplitude 2 will be basically K and 1 over this time around R will be what, 2.5 wavelengths. So 2.5 times 12, right? 2.5 times 12. And K is this value, right? So that gives you a direct calculation. So 6 times 3 times 10 to the power minus 5 divided by 2.5 times 12. Yeah. So how much is that? What's the new amplitude? I don't have a calculator. Huh? Oh, so they say point source here. Take it as a 3D point source. That will be water wave. I think I went through that on Sunday, but I know you had another exam on Monday. Um, but let me just check it out because there was this big stupid question on Sunday. One of them was asking, so annoying because the kind of like the whoever set the paper just assumes students understand what this point source on the water surface means. Let me just yeah, it is. But yeah, that was this thing here. Yeah, it was this thing here. Hang on. Yeah. So I think the student was very confused by the answer key that the school gave. It was like power over pi SD, where S is like the depth of the water, which is utterly ridiculous. And then yeah, it's not something within your syllabus. Absolutely not something within your syllabus. What happened was I went to pull out historical records of where the question came from. So the question originated from RI in 2013, right? Where it says that the energy of the wave is spread over the entire circumference of the ripple. Like at least the RI paper, they did give a bit of context of where the water wave was the energy was concentrated at. It was concentrated on the ripple of the water. So intensity for these calculations here is power over 2 pi r, which is circumference of the ripple. So this particular example is the example where it's a point source, but the energy of the wave is focused on the circumference. Okay, to be honest, so far, after all these years, I mean 12 years, um, I've only seen 2 versions of this point source thing. Number one, water surface. Number two, 3D point source. Like, I don't think they do like, they have any other versions. Yeah. Okay lah, not 12 years lah. I mean 25 years. I mean since my time, right? So I've never seen a different version. But the problem is the way that they ask it. So I was very annoyed by that particular question because the question said something like, uh, waves radiate uniformly from the dippers in all directions on the surface of the water. And then, oh, hang on, sorry, I need to log in again. Okay, sorry. Waves radiate uniformly, yeah, in all directions, right? So what happens is that I was very annoyed by this question because the question did not do the same thing as the RI question did, right? Even RI gave the students some context. Energy is, spread evenly throughout the circumference. This one didn't. And what happened was the calculation was based on that, right? I think the other student that was on Sunday, she thought that the energy was spread out as an area like this. So she thought it was spread out as pi r squared. Yeah, but that's the thing, right? So that's why I had to pull out the RI thing, the RI question, to show you that the question originated from that context where the energy is focused on the circumference. So what happened was the mark scheme for this, right? The mark scheme, whoever set the exam paper said that, oh, students should be aware that power for water waves, right? Deeper water waves, power is divided by pi sd, where s is the depth of the water, right? And since the depth of the water is constant, I think that's what the answer key said, right? So then it says intensity is therefore proportional to 1 over d, which is ridiculous. Okay? So therefore I tell you that if anything is this, right? This particular concept here, right? Power is concentrated on the circumference. And there's only two versions, circumference and 3D. That's pretty much like, all the two possible scenarios for this. Because you're asking me like, how do I know whether it's 2D or 3D, right? Yeah. So if they say point source, you take it as 3D. It's a sound wave, so you can take it as 3D. When I speak, sound is spread out three-dimensional. If it's a water wave, water surface, then the wave is concentrated on the circumference. And these are the only two versions I've seen so far. Yeah, yeah. Uh, yeah, I don't think so unless they come up with some nonsense. Honestly speaking, I really cannot safeguard against that because I can't think of any question. I've never seen any question where they say that the energy spread over the area of a flat circle. If they did, it doesn't make sense. No, 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 no. It's 2 pi r. Yeah, it's 2 pi r. If it's pi r squared, it will be you end up with the same calculations as this, because the only difference between flat circular area pi r squared and this is 4 pi r squared. This is the surface area of a sphere. Point source spherical surface area. Yeah. Yeah. So for that particular question, I mean, just in case, because I mean, don't know whether you've got time to look at it, but so for the particular question, so it turns out that, let me see, okay, turns out, oh, oops, sorry, sorry about that. So it turns out, so if the intensity is inversely proportional to 2 pi r, then the amplitude is inversely proportional to 1 over root r. Yeah. Yeah, that would be the case for this. Let me just 1 over root r. Let me see first. Let me see whether I wrote it down somewhere. Yeah, there we go. Right. So yeah. So there's only these two versions, right? Flat circular water ripple, right? Intensity inversely proportional to pi r. Amplitude is proportional to square root of 1 over r, right? And then there's a 3D point source, which is inversely proportional to 4 pi r squared, and then therefore amplitude is inversely proportional to r, no square root. Yeah. Mm. So anyway, back to this one here. So what's the number for this? What's the value for this? Did you punch it in already? Yeah, no worries. okay, so 5.4 times 10 to the power minus 3, right? So it's a, huh? Wait, what's going on? No, that's even bigger amplitude now. Then divided by 2.5 times 12. Yeah, divided. Yeah, that's okay. Which is 6 times 10 to the power minus 6 meters. Yeah. So basically what happens is that when the, like, just right next to the source, right, the amplitude here is 3 times 10 to the power minus 5. And then when the wave is reflected, it's 6 point times 10 to the power minus 6. And I think the question now would be, what's part two? Why is not a complete no displacement? Okay, no worries. Yeah, I mean, okay. Yes. Yes, yes. And therefore the amplitude is less. Yeah, 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 yeah. But yeah lah, okay lah. I mean whatever lah, right? But I'm quite pretty sure that they'll probably ask you why the node is not a complete zero intensity, right? And that's because there is residual amplitude, like as in it's not a completely destructive. Like the node will be completely destructive interference, right? So since you have two waves like approaching each other at the position of the node where the amplitudes are not equal to each other, so you will get non-zero amplitude and therefore non-zero intensity at the node. Yeah. Okay. Uh, next one though. What's the next one? Next one. Sorry, I'm trying to figure out where my Telegram is. Wait, okay. And we got the quantum one. Let's try the quantum. This one, huh? Okay. So you did the calculations. Careful, no units here. You minus one there though. Oh no, sorry, I didn't see the joules there. I thought you didn't write the units here. Sometimes, I think most of the time, yes. But never assume though. Actually, yeah. Uh-huh. Oh yeah, yeah, yeah. Okay, so I'll just tell you this. Please remember that all physics equations are SI units. Like every single physics equations are always SI units. Like, yeah, that's what the SI units are for. Yeah, it's like everything is SI units. EVS is a shortcut unit. Yeah, EVS is shortcut, right? Because it's electron volts. It's easy. Like if you have 0 volts and 100 volts and you have an electron and the electron is attracted to the 100 volts and it passes through the hole, then what's the KE as it comes out, right? It's 100 ev, 100 electron volts. Yeah, it's a shortcut, but it's not SI. So if let's say I ask you, so what's the speed of this electron, then if you want to find the speed, you need to 100 ev times 1.6 times 10 power minus 19 to convert it to joules, and this equals to half mv squared, where m must be in kg and v will be in meters per second, right? Like any physics equations that you use will always use SI units to do the conversion. Yeah. Um. Okay. For C, okay, let's look at this. So which one was the original one? This black one. Oh, the bottom one. Okay, okay, the bottom one. The black one there is the one that you drew. Okay, hang on. No, I need to check. So frequency is kept constant, but the intensity is doubled. Then it asks you to sketch the thing for this. Okay. Oh, I keep shifting this around. So annoying. Sorry. Ah. Okay. Um. don't know whether you remember this in quantum. I was doing quantum, so in quantum, the intensity equation, you see, intensity, right? Intensity is a trigger word in quantum physics, right? Because you should be triggered. You'll be like, okay, you're asking me about intensity in quantum. So intensity is power over area, just like what we did, okay? And then power is, but like, shortcut to everything, power is essentially just N over T times HF over A, right? Yeah, don't know whether you remember this. So this will be the rate of photons, and this will be the frequency, like the color, right? Frequency will be like the color. I mean the type lah, right? High frequency is like violet. So they said that the frequency is maintained, but then the intensity double. So what are you changing up here? No, I mean you're changing the intensity, yes, but intensity has two factors. We are keeping the frequency constant, right? But then we're doubling the intensity. So what do we increase? Rate of photons. Rate of photons, right? Rate of photons. So rate of a variable of photons. Yeah, that's right. The thing is this, some students do forget that intensity has two factors. So whenever they say intensity doubled, then they just think that everything doubles, right? If you keep the same frequency, the stopping voltage is still the same. Because the stopping voltage is dependent on the energy of the photon, which is dependent on the frequency of the light. Okay? So it will have the same stopping voltage, but you have double the rate of photons, means you will have double the current, right? Double the number of electrons, sorry, photoelectrons. So whatever number of grids that you have here, you double that. And then the graph, you draw it like that. So hmm, yeah, so because we keep the frequency the same, right? Yeah, frequency. Like what some students also do confuse, they think that frequency and rate is the same thing. It's not. So when we talk about quantum, frequency is literally the type of wave that you're using, right? You could have red frequency, blue, green, yellow frequency. Frequency talks about the color. Frequency is the color or the type. Okay. Um, I mean, UV is not a color, ultraviolet is not color, but ultraviolet has very high frequency. Infrared has low frequency, right? You understand the spectrum, right? Okay. So the idea here is HF. What does HF stand for? Of one photon, right? So if your incoming photon is like that amount of energy, like this is like HF like that, right? And then you have this piece of metal which is a certain work function, right? Which is a certain work function, and then your electron comes out, your electron pops out like this, okay? Electron pops out like that. It has a certain amount of Ke, right? Yeah, I mean, yeah. So basically, Ke is what here? Ke is basically HF minus phi, right? The incident photon energy minus weight of a function, that's the Ke, right? So if you maintain the same Ke, maintain the same frequency, then you will have the same Ke of max Ke lah, right? Max Ke of the photoelectron. So even if you double the intensity, even if you double it, the Ke of the electron doesn't change. Yeah, so which also means that on this side, the stopping potential is still the same as before, right? So that's to answer why is the stopping potential is the same again. But then yet when we talk about saturation current, and current is the rate of flow of electrons, okay, it will depend on how many electrons are being emitted. So if you increase intensity, if you double intensity, but you didn't change the frequency, it just means that the N over T is doubled. That means you have twice the rate of photons. You have 2 times the rate of photons, like twice the amount. So you will have 2 times the number of electrons, and therefore the current inside, right, inside here, the current, I is equals to N E over T. You are doubling the electrons. So the current here, the saturation current, will be doubled. So it will go from, I believe this is 8 units, then it'll go to 16 units. So somewhere around there. Yes, absolutely, yes. That's the exact thing that you're talking about. Yes. Yeah. Sorry, I need to mark it at 16. I don't know where 16 is. Can't really see shit here. Hang on. This thing's a bit small for me. 16 is there. So somewhere around here. Here to here. Yeah. So your graph should reach that point, and then it needs to be a straight line under 16. Like this. Yeah. There we go. So yeah, yeah, you should. Yeah. Yeah. You should. Yeah. Um sorry, one more time again. You're not wrong. Oh, you mean oh, okay, you mean this one here. I see. Uh well, I mean the I mean if you do write this, in my mind, I'm thinking if you didn't change the incident light, then the stopping potential is the same. So I had no qualms with this equation. That means your that means I thought you were writing that because you're trying to show yourself that you had the same starting same stopping potential. You know what I mean? That's why I wasn't too concerned about that. But I was concerned about the graph here because the graph you see, right, you shifted the graph backwards. Yeah, so if you shift it backwards, I'm like, oh, did you think that the stopping potential has increased, right? So no, the stopping potential did not increase. Yeah, because we are using the same frequency. But yeah, I mean, it's like, okay, I mean, I'll draw it out for you. You see, this is constant, right? The frequency is constant, right? The work function still the same piece of metal, right? So stopping potential is still constant. So yeah. So this equation is, I mean, it's legit, right? Yeah. But I think it's more like the intensity. I think it's one thing to write this thing, it's another thing to forget about this. This is easily forgotten. I have no idea why. I I suspect like the schools don't really emphasize on this. Like when I teach this, right, and then I think some students will be like, I've never seen this before. No, then they glaze over, right? Then it's like, but this is like such a super thing, super important thing because it happens all the time. This question here, like it happens all the time. So you have to know this like really well. Yeah. Um, but I'm looking at part D now. That looks a bit more complicated. Let me see. The same electromagnetic radiation in C is now incident on Q. Given that the stopping potential for a photoelectric emission from metal Q is 1.8 volts, sketch when incident on Q and label it B. Okay. So, what was the what was the stopping potential of the first one? No, no, 2.3, 2.3. So then they're saying that the no, but this okay, hang on. Oh, but then the next one is 1.8. Same same radiation, same frequency as the previous one, but then the stopping potential is only 1.8 now, which suggests that work function of Q is oh man, I can't see this shit. I'm gonna write it down. So HF equals to phi 1 plus E 1 point, no, sorry, 2.3. You said 2.3, right? Okay. Then same HF equals to phi 2 because I need to figure out what's the new work function. Do I need to? Actually, I don't need to. I don't really care. I just start from 1.8. I just draw the graph from 1.8. Okay, anyway, so plus E 1.8. Technically, yeah, I don't need. I just need to draw the graph. Stopping potential from 1.8. I just draw it from 1.8. 1.8, that means the other graph will be starting from here, like this. But I'm a bit concerned. So same as part C, intensity the same. Oh, yeah. I mean, yeah lah. So you can start from 1.8, but it will reach the same level as the first one. Something like that. Oh man. Okay, wait. Let me just double check everything again, huh? So you have a same in C. That means double intensity, stopping potential, same in C. Stopping potential is 1.8. I would think that the rate of photons is the same. So I would think that the rate of electrons. I don't know. If they come out with some weird ass graph, I'll tell you that it's probably taken out of context. So for part D, they have used a different piece of metal with a different work function, but the rate of photons is still the same as part C. Ah, that's not good. Yeah, that's fine. What in the damn hell? Wait, what? Why they draw it the other way around? Shit. What are these people doing? Okay. Oh, sorry. Um, Based on the answer, like I know it's hard for you to look at the question, but now I realize that they have two planes. P is on the left side, Q is on the right side. They switch the direction of the light. So now they're saying that the light is shining on this side. Is that it? Yeah, because I mean I only have this part of the question, right? I don't have like the front part. Yeah. So I mean you show me the answer and I'm just like if it's the other way around, it just tells me that, because like yeah, Q is on this side now. Yeah. Yeah. Q is on this side now. And yeah. Yeah. So it's flipped over to their side. But then it also takes 16. Yeah, it will also take 16 units. Below it, it's kind of like this. Hmm. So you have to look at the setup, right? Yeah, I believe P was on one side, Q was on our side. So if they switch the light and shine it on Q, then the electrons are going the other way around, right? The electrons are going towards P now. But they're saying that in order to stop the electrons from reaching P, what they do is they make Q positive to pull the electrons back. Yeah, so I mean, but this is a quite out of context question, like, yeah. How many marks was this? 2 marks. So if you had drawn from like 1.8 and then you had drawn to the same level, that would have given you 1 mark lah. Obviously, the second mark was to draw it upside down. Yeah. I mean inverted. Y- Yes. Yeah, it's fine. That's right. That's fine. Yeah. It's okay. Don't worry about it. Yeah. Essentially, uh, okay. So don't get sucked into the whole negative sign thing, right? Think of it in terms of energy accounting, right? So yeah, think of it as energy accounting, because if you were to sub in negative here, you will get it wrong, right? And you might not even realize, because like you have this number minus with another number, but okay lah, you will get a negative value anyway, so it should be quite obvious. Um, but you'll be stuck lah. You'll be like, how come the negative sign don't works? Um, okay, so I'll explain this a bit. Hang on, I just need to. I'll explain this a bit. Okay, so I'll use this to explain. So you understand that the kinetic energy of the electron is positive, right? It has positive value. The stopping potential is negative because you're trying to stop the electron, right? Okay. Um, so as the electron flies over, it loses Ke, right? But it gains EPE. So the electron fly over over here, the Ke is 0 right before it touches the plate. Okay, so loss of Ke is equals to gain of EPE, right? And the loss of Ke will be, I mean, final minus initial, 0 minus um, Ke max equals to gain in EPE, right? So let's say we consider 0 volts and that's negative volts. So it will be electron times the change in potential will be negative V minus 0, negative Vs minus 0. That's our thing, correct? Yeah. So you will end up with negative Ke max is equals to negative EVS, and both sides cancels off, right? So that's why there's a negative sign, right? That's why there's a negative sign. But I think what you suggested is correct. It's not that you're trying to force it to work. It's more like because there's a negative sign to indicate a loss of Ke, and therefore it will work. You get what I'm saying? Yeah. So we're not like intentionally manipulating the equation, the numbers, just so that it will work for us. It's not that. It's just that because there's a loss of Ke, or there's a gain in negative EP. There's a gain in EP but negative EP, right? And therefore you end up like it will work like in a sense. Your working was what? I was trying to see your working here. Yeah, down here, right? So, like you're asking how come we don't put the negative sign into this, right? Yeah, that's pretty much the reason why. Um, I will suggest to you that if you write this equation, right, it seems like you are are taking this from somewhere. There's a EVS that keeps appearing here, right? You wrote it here and you wrote it there. It gives me an idea that you're reciting this from memory, right? No, which is fine, but now I want you to make sense of it. Because like I mean, if you want to be able to solve all these questions, like after you memorize it, you make sense of it. So always remember that EVS is really the Ke max of the electron, right? It's really the Ke max of the electron. So you can replace EVS with Ke max. That's what I just showed you, right? The working. So what I like to do sometimes, most of the times whenever I do this kind of quantum questions for myself, I like to rearrange it so that it looks like this. So Ke max is equals to HF minus phi. I like to write it like that because it reminds myself that the electron, right, the amount of Ke that it has is basically after it absorbed the photon and then minus off the amount of energy needed to come out of the metal, the work function, then that's the remaining energy that it has. So this is it, residual Ke. Like, but that's my way of yeah, that's my way of understanding it, lah, right? Like like yes, different people have different ways of understanding it. Some people like to think of it as, oh, if I work backwards, the Ke plus the work function equals to the original the original
energy of the photon, which is fine, you know. So I'm just introducing you this way, right, of understanding it. So, but if you do write it this way, you can also understand it yourself. You can say that, oh, the photon energy, right, is used to overcome work function, right? So the electron can come out. The electron has a Ke, but then the Ke max that the electron has, we're going to try to stop it. So we use EVS to stop the electron. So, you know, this equation would then make sense to you, right? So whichever way you want to is fine. To memorize it is fine. I think it's more like make sense of it, because once you make sense of it, then suddenly everything, you know, works. Yeah, exactly. Yeah. Do you know this EVS? Where does it come from? Yeah, Q del V. That's right. Exactly. It's a work done, lah. Yeah, work done when the electron moves to the negative plate, it gains EPE. Yeah. Okay. Wait, there seems to be one more. This pendulum one. Okay. Oh, geez, pendulum. Oh, I hate pendulums. Because pendulums are always gonna be like some approximating crap. Let's see. Let's see what's this all about. Oh, it's a image scan. Oh, it's an image scan. No wonder you can't search. Is that right? You can't like actually highlight the words in your document. Yeah, yeah, yeah. They probably just scanned it. Okay, what's going on here? Horizontal displacement 8 cm from rest position, supported by inelastic. Mass is 120 grams. Rises vertically. When it's released, it swings, performing simple harmonic. So they did, you know, they kind of like did declare that it is SHM, so we don't have to say that, oh, it's not. So it is. Then for the motion of the sphere, show that the total energy of the sphere is this. I mean, since it's SHM and you know it's this one, so it's just half m omega squared. X. Ooh, what the heck is X naught? Yeah, that's gonna be my concern. Sheesh, X naught squared, right? Do we take? sh- Yeah, no. So yeah, I mean both ways works, right? So X naught is gonna be a pain point, right? Do we take the horizontal or do we take the the hypotenuse, right? I don't know. I don't know. I have no idea, right? I what I'm trying to contend with is by definition SHM, the the displacement should be parallel to the direction of the accelerations, right? So, you know, when a pendulum does SHM, we approximate it to be a horizontal motion. That means it goes back and forth horizontally. And if that's the case, then I should just take 8 cm as the amplitude, and then I just calculate the thing based on 8 cm. Like I'll take 8 cm and I'll put it inside here. Oh, omega square would be, damn. Ah, yeah, you're right. So it's just MGH. The total energy is just MGH. Because yeah. Because I don't know what omega square is. Yeah, you're right. I mean, I I don't know what omega square is. You're right. I mean, if I try to figure out omega square is not there, then realize, oh shit, that means it's MGH. Okay, second part, the frequency. So the total energy is half m omega squared x naught squared. Yeah, equals to MGH. Yeah, that's right. Yeah. But I would take x naught as 8 cm. I believe that's the case. No, as in like the fact that we are only considering the horizontal displacement is because of small angle approximation. We consider that the vertical gain in height is negligible to the horizontal displacement, like 0.4 compared to 8 cm. We just take it at the amplitude as 8 cm. Oh yeah, I mean, what happens if you take 8 squared plus 0.4 squared and then you square root it? I think you get something very close to 8 anyway. Yeah, yeah, yeah. So small angle approximation, the amplitude is just 8 cm. Oh, okay. No, no, 4 for 2, 2, 2, 2, 2. Yeah, 2, 2, 2, 2, 2, 2. Yeah, yeah. I can't remember that. I memorized all of them, right? So goodness. Shoots. Where is it? Probably have to. Cause I teach two streams, right? So I have no idea what is included, what is not included in both sets. I usually just memorize the whole damn thing. So it's easier for me. It's not. It's not. I think only the V is included, right? The one where you say omega square root thing and all that. Yeah. So you probably have to quote. Yep, you're right. Yeah. So it's half mv squared. Yeah, this one here. Then you get half m omega squared x naught squared. Yeah. Pretty sure it's the equation that you can quote. So you don't have to show how to derive this equation. You can just quote it half m omega squared. You probably might have to write down total energy of SHM is half m omega squared x naught squared, and then probably have to write a statement saying that pendulum is approximate SHM, so x naught is taken as 8 cm. I would write it like that's my recommended thing, because I just noticed this is an A level question. Yeah, this is an actual A level question. Yeah, yeah, yeah. Mhm, mhm. Clues. Oh, oh, okay, okay. Yeah, sure. Yeah, sure, sure, sure. I mean, that's all good, man. Hang on, let me just um paste it onto my PowerPoint. A lot easier for me to just take a look at it. This would be nuclear fission. Fission. It'll be fission. And they want you to find the power release. Oh, okay. So we're trying to play detective here. Trying to figure out what kind of cryptic message she's trying to say. Um, okay. Okay. Oh, there's no wait, hang on. Are you talking about like the multiple? Like the 2n? Okay. Yeah. There's no 2u. What? If there's a 2 in front, and then the way that we calculate the what? I have never heard of that. This one? Uh-huh. Okay. No, no. Wait, let me think first. Uh, I mean, it's interesting, but no, because the moment you mention limiting reagent, then something clicks in my head. Uh, okay. Sorry. One more time. Can you kind of like describe what she said again? Mm-hmm. Okay, okay. Let me think first. Hang on. Hang on. Wait. Oh, okay. Hang on. What was this about? So you put a star here. Is it a star? Okay. Okay. So okay. Now I'm just trying to understand what this woman is saying. Uh, so this is in case there's a 2 in front of the U plus N. Yeah. And then you're saying that this is it gives you lithium and molybdenum. And then you say if it's the same 1.2 moles, is it? 1.2, which is your times 10 to the power. Okay. So the number of U is equals to the number of N is equal to star, then star divided by 2. Well, I know, I guess, but it's more like it sounds a bit cryptic. I mean, we're spending the time now trying to figure out what she's saying. It's just that I did encounter something with my other side. Hang on. Uh Wait, let me is something that I have. Let me just quickly check. Okay, so no, don't worry about it. Yeah, this one here. So this is something I had on the other side. So fusion in the sun is basically two protons right? I mean, there's a big 2 in front, you know? So I'm just wondering whether this is related to what she's saying. And then the thing will actually give you a deuterium, and then you add on 1 deuterium to a proton, then you get a 3 2 helium, that sort of thing. I don't know whether or not to kind of like to make a guess that she's not going to do fission. She actually will be doing fusion, which is this one here. What? No, but fusion is about the same, right? What she's referring to is the like the way we count the numbers. Your friend mentioned what limiting reagent, which I don't. I mean, if it's limiting reagent, then they'll probably tell you like, oh, I have this number of A, like say for example A and B, like 2A plus B gives me C, for example, okay? Like, like let's say for example, I have this amount of A and I have this amount of B, right? Let's say for example, like 2A will react with B, right? Let's say I have 100 Bs, okay? And then A I have like 500 for example, right? 500 As. How many reactions can I get? I won't get 500, right? I will get only 100 because B is my limiting reagent. In that sense, I mean, if that's what your friend is saying. But then the question will have to give you both, right? The question will have to tell you that there is this amount of A and then there's this amount of B. So you have to then check which one has less. Then that's your limiting reagent. I mean, that's all there is. I understand that one was chemistry last time, right? And sounds like you have PTSD from chemistry. Uh, but yeah, I mean, if this makes sense to you, then if that comes out, then that's the way to do this. Yes, that's right. You take the lesser because okay, so in a sense, right? So let's say you use up 100 B, right? How many A's do you use up? You use up at most 200. You basically have 300 of A like left over, like doing nothing. Yeah, yeah, yeah. Like yeah, that's sort of thing lah. Yeah. So you won't get yeah, you won't get 500 A's. Wait, hang on. So my concern now is your teacher comes up with this nonsense. Then stay at NY lah. Uh, yeah, if you're very good, then why do you get kicked out? I don't know why people like to brag like that. I don't understand. Like I'm here trying to figure out stuff, right? Like it's always a constant thing to trying to figure out stuff. Why would you go around telling people like oh I'm the best? What? I don't have that kind of skin, right? It's kind of weird. Okay, so essentially I'm just gonna tell you what happens here, okay? In case it comes out and you see it and you're like, what is going on? Okay, so fusion in the sun, um, long story short, is basically two hydrogens, okay, fusing and becoming 4 2 helium, right? If you look at the first stage, two hydrogens, right, and then become 4 2 helium, right? So tomorrow is what paper what paper 2, okay. So data response question, right? There's a possibility for this, okay. All right. So that's the overall picture of this one. But it turns out the question is, um, like it looks like it's okay. So this is a proton, right? One hydrogen is a proton, right? And then 2 1 hydrogen is a deuterium, right? It's still hydrogen, right? But this one has one more neutron. Okay. Sorry, let me just try to explain this in a way because so you got two hydrogens. If you just look at the start and all the way to the end, it's basically you combining these two. No, sorry, you're combining two deuteriums into a 4 2 helium, right? 2 deuteriums into 4,2 helium, right? You know, right? The end product is your end product is helium. Okay. Uh, you also do get like 2 protons left over. Okay, what happens is this. So stage 1, 1 proton gives you 1 deuterium. Right, I'm going to write deuterium here. Okay. Second stage, 1 proton, 1 deuterium will give you 3,2 helium. Okay, right. So in a way, right, how many protons have we used? 3 protons. So we have used 3 protons, right? Okay. Then the thing about this deuterium, the deuterium is being used in the third stage here, right? You see the deuterium is being used in here. Sorry, the 3,2 helium. So the 3,2 helium is being used in the third stage here, right? But then yet there's another one. So this second one came from another set of stage 1 and stage 2. Correct. 6 protons used in total. Very good. All right. And then you form the 4,2 helium, which is the end product. But in return, you get back 2. So overall, a stage 1, 2, 3 process, how many protons in like, how many protons net did we use? 4. Yeah, 4. 6 minus 2 is 4. I mean, like, this has happened in some prelims before. Like, I think maybe couple of years back, I saw one of the schools do this, right? And everyone was just very confused by this. But in case it comes out tomorrow, this is what we are doing. You're just counting the number of protons. Yeah, it's very silly, right? Fusion, oh, they'll ask you like, how much fusion, how many hydrogens have been used. Yeah. Like, I mean, the actual question here was like you don't have to care about it because the rest of it is yeah, it's essentially this one here, like so for a complete set of stage 1 to 3, 4 protons has been converted. And then this one is from my IB side, so they had to do this thing called astrophysics, and they have to go and calculate the luminosity of the sun, all these kind of things. But that was not what that I mean. That's why I'm not showing you. I'm not going to explain this part to you because it's kind of not your concern. But it's only this part here. Like I've seen this question come up before. Like the equations come up before, and then the way to count the number of protons is really by what we just did. Yeah. In case your teacher is going through something like that. Yeah, because number, right? It's talking about the big number. Okay. Mass defect. It really depends, right? Cause mass defect has like there are like a few versions of it. Um, you have protons plus neutrons, and then gives you the element X, right? Then you have decay, which is X decay via alpha particles to something, plus alpha, right? And then you have X decaying by beta, right? Then 0 minus 1 E. Do you need to draw the neutrino? Don't need. Okay. Then you have gamma radiation, right? Something like that. Okay. Then you got fusion, fusion being something like that. Then you got fission, right? Um, Fission being this barium and then krypton and then 3 neutrons, right? Something like that. Okay. So yeah, so um forming constituent nucleons, forming from constituent nucleons, the whole of decay, right? And then you got your fusion and you got your fission, right? And essentially all of these processes that I'm showing you here right now, there's basically energy being released, right? Right? So energy is released, right? And it's not supplied, okay? So so if it's energy release plus energy plus energy plus energy and plus energy, then if you get energy released, it's definitely got mass defect, right? So that means the total mass here, right, and the mass on the other side, yeah, the mass will be more, right? So what you can do is again basically like mass 1 minus mass 2, right, equals to mass defect, right? And mass defect is the triangle M there, right, down here, right? This will be mass defect here, right? So you take the total mass. Then the other thing is that most of the times they give you the mass in U. So they give you like in like number U, number U, right? So that's the atomic mass unit. So if you have the mass defect in U, you need to convert it into mass defect in kg, right? Like this, you have to convert it to mass defect in kg. Then you use E equals mc squared, right? So when you use E equals mc squared, again remember that it's technically E equals to del mc squared. No, yeah, no, no, it is. No, as in like, not can you, it is. Now, okay, so you have to be very careful there, right? So I mean, when we do any nuclear reaction and energy is released, right? I think my first question to you is, where is this energy coming from? Like what creates this energy? Yeah, correct. So basically, this mass defect, right? We take the mass, we convert it into pure energy, right? Yeah. So then we use this equation. So it's not that you can take this E as it is exactly this one. Like no, this thing here is being calculated here like that, right? Okay. So with regards to your statement about binding energy, right? With regards to binding energy, so you have to go back to your definition of binding energy. What's the definition of binding energy? Separate a nucleus constituent nucleons. I think I would want you to use the word nucleus and nucleons. Yeah, separate the nucleus into its constituent nucleons to infinity. That's binding energy, right? Yeah. What's the other version of it? Yeah. There's a second version of it. So binding energy is the energy released when a nucleus is formed from its constituent constituent nucleons. Do you realize that I just said whatever you said in reverse? Yeah, right? Okay. So based on that, right, out of all these things here, only one of them is classified. The energy is classified as binding energy, which is this one here. Yeah, yeah. So the term binding energy, strictly is only for when you are trying to create the nucleus from its constituent nucleons. So let's say for example, I ask you something like, um, I give you something like, hang on, let me just do this. Let's say I give you the, let's say I give you uranium. Oh yeah, yeah, sure. I mean, hang on, wait, I'm not done yet actually. I'm just trying to. Oh no. It's fine. Don't worry about it. Okay. Uh, so let's say they ask you something like, oh, find the BE of uranium 235. Right? Let's say they ask you something, oh, find the BE of uranium, the binding energy of uranium 235. What you will need? 235, 82? Is it 82? Hang on, let me just Google this up. So uranium 235 has how many protons? I'm so bad at this because my chemistry is so shit. 92, sorry, 92, not 82. Whoops. 92. 92. So what would you have to do? You have to take 92 protons plus 235 minus 92 is how much? Shit. Never mind. 143 plus 143 neutrons to give you your 235 92 uranium, right? Then you basically have to find, like they ask you to find binding energy, right? So you have to find the total mass, right? And then the total mass. I mean, whichever bigger, whichever has a bigger mass. No, in this case here, products, reactants will have bigger. Sorry, yeah. For this case, definitely reactants will have bigger, right? So this side here will have more mass, right? And this is equals to the mass defect, right? Then your E equals to del MC squared, MC squared, and this will be the binding energy of, yeah, yeah, yeah. Okay so far? Can I? But I'm not done yet. So if they ask you some random question where they say, oh, go and find the binding energy of this nucleus, you do this, right? You split it into its protons, neutrons. Because when they ask you for binding energy, they're asking you what's the energy released when, right? I mean, energy is released here, right? That's the energy here as well, right? That's the energy released when the nucleus is formed from its constituent nucleons, protons and neutrons. Okay? Because there are sometimes they will do a different question, right? So if you go back to this one here, sometimes let's say for example they give you a fusion, no, maybe a fission, yeah, fission reaction here, and then instead of mass, so some question they don't give you mass, they give you BE values. They give you the total BE values. Wait, I just move this up a bit. Goodness, move faster. So slow. Yeah, let me just move it up a bit. Okay. So sometimes they give you BE, right? BE, and they give you BE per nucleon. So you have to take BE per A times A, right? And then you have to take the yeah the mass number times A, and then the BE over A times A, and then you have to calculate like the total BE. Like you find the total BE, right? Okay. Wait, let me just move it up a bit more again. Right. Then you find the total BE here, and then total BE. Yeah. So the bigger minus the smaller, you will get the energy release out, right? The difference, right? But like I don't know whether you remember this, but I mean, just remember that. Don't be surprised. So we know that this fission releases energy, right? If you compare the mass, and when you compare mass, you need to take the mass here and the total mass here, right? The mass versus the mass, right? The total mass there, right? Like, do you understand that the mass of the products is actually less than the mass of the reactant, right? Oh, sorry, the fission should be a plus one neutron also. Sorry about that. Forgot a plus one neutron. Okay, yeah. So the total mass of this side, the left hand side, will be more than the mass, like barium, krypton, and three neutrons added together. Therefore, you get mass defect, and therefore you get energy released, right? But when you calculate using binding energy, right? Number one, don't forget, standalone protons and neutrons do not have binding energy. Only these ones, the nuclei, the compounded nuclei have binding energy, right? So then you can calculate the total BE, and the idea here is the total BE. If energy is released, the total BE value, the number is actually a bigger number than this, than the reactant. So it will be something like that, right? The BE will have a bigger value if energy is released. The mass will be a smaller value if energy is released. Yeah, okay. So we went through that before. Yeah. No. For everything, everything here. Yes, everything is here. That is. Yeah. So yeah, just be very careful of like, I think mass defect is not so scary. Actually, binding energy is scarier because there's a stronger tendency for students to get confused about what they're asking for. Why are they asking me for binding energy, right? So one more time, just to summarize, if they ask you what's the binding energy of a nucleus, right? You go back to its constituent nucleons, protons and neutrons. If they say that, oh, I have a reaction, a nuclear reaction, can be any one of these, and they give you the binding energy values, then your job is to find the total BE on one side, total BE on the other side. Standalone protons, neutrons do not have BE, right? And then you check the difference in the BE. That will be the energy released. Yeah. Sorry, what? Oh yeah, no, no, yeah. I think mass defect you just have to remember to convert it to kg. Yeah, yeah. You just have to. Yeah. Yes, yes, yes. Yeah. If let's say for example there's three neutrons here, right? Then yeah, like, you have to multiply by three neutrons. Like there are three neutrons. Yeah. Yeah. Mm-mm. Mm. That's right. Yes, that's right. Yeah, yeah. Yeah, what's up? Yeah, yeah. Okay. Okay. Hang on. Let's see. Yeah. 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 So it's working. Yeah. So the thing is that yeah, this is reverse engineering. It's working backwards. Yeah. 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 Wait. So what you want to do is I mean, they say binding energy per nucleon, right? Binding energy per nucleon. So what you want to do is you basically, so you need to recognize that this mass defect of this one here, right? Like what are they referring to, this mass defect? The mass defect here is like the amount of mass defect when you form uranium-235 from its constituent nucleons. It's a bit weird, but they give you the mass, then they give you the mass of the nucleons, then they help you to go and find this 1.865, which technically is just this minus this lah. Oh, sorry, this one, separate nucleons minus away this one, and then you get 1.865. Yeah, yeah, it's a bit weird, but that they're showing it, they're doing the math for you, right? So if you do this mass defect and then you convert it to kg, and then you E equals to mc squared, right? And then you get energy in joules, right? Then you convert it to energy in MeV. Yeah, that's right. Right, you convert it. Yes, it is. Yes, it is. So and then on top of that, this one here at this point in time will be total BE, right? Total BE. But then you are supposed to find, yeah, divide by 235. So total BE divided by, so it's not straightforward because you have to do all sorts of calculations here. But total BE divided by 235, it will give you this number here. Yeah. Mm. Yeah. Remember there's a shortcut, right? So if you remember, I think we did a calculation, it's 933.5, I believe. Like if you, for every one mass defect, that's equivalent to 933.5 MeV. No. But it's for us to check lah, you know. So I believe like based on I think during the nuclear lessons we were doing, like I was just telling you all that please remember there is a shortcut, but you're not allowed to use it. I have no freaking idea why, right? They're just being very annoying that way. Hang on, I say that, but you know what? Let me just double check the values, okay? Let me see the constants. Yellow. It's just freaking annoying. So they didn't convert it for you in that sense. Yeah, they didn't convert it for you. Hmm. But I mean, yeah. So if you do 1U of mass defect is 933.5. So it's 1.865, right? So 1.865 times 933.5, then you divide by 235. You should get this. Yeah, wait, let's so 1.865 times 933.5, right? Then the answer divided yeah, yeah, divided by 235. I mean, if you don't have the show working, you can do this so 7.41. Yeah. But that's the magic number, and yeah, that's the magic number. Yeah. Mm. Yeah, it is. Because you see, right, the conversion from E equals MC square, convert to joules, convert to MEV, and then get that's a very standardized conversion. Like it's always the same numbers, it's a constant. So so mass effect of 1U should give you a constant, which is this 933.5 mega electron volts. So if you didn't have to show the working, you could have just plugged it inside here. But same number of SF, so that means you should have written 7.408. Mm, yeah. Okay. Yeah. Yeah lah. Good. That one is good for checking lah. Easy to use for checking. Okay. All right. All the best. No worries. Just kind of like keep trying to figure out what you're still shaky on and all that, and then we try to fix it after that also. Mm. How long is the paper again? 2 hours. Well, it really depends, because like I mean, I will look at the data response and I'll be like, is this going to be a big waste of time? If it's a big waste of time, I would say what 15 minutes. Yeah, yeah, 15 minutes. If it's a big waste of time, if it's something that you realize that actually can do, right? Then be a bit more time lah. Yeah. How many marks again? Sometimes is it 20 or 25? Total is 90, is it? Total is 90. Data response is so non-official exams, right? Non-official exams is like the it can change one, right? So total is 80 marks, sorry. 80 marks. Data response is 20. Yeah. Wait, no. So what you want to do is this. You want to take your 2 hours, right? You want to take your 2 hours, then divide by 80 marks. 2 times 60, 120 divided by 80 marks. Yeah, like 1.5 minutes lah, huh? So it hasn't changed. Yeah, 1 mark 1.5. So 20 times 1.5. So it's supposed to be 30 minutes, right? Half an hour. But generally speaking, DRQs are usually like is based on time management. So let's see. Yeah, this kind. Oh my God, look at that. Yes. Hmm. No lah. It really depends on how you want to play the game, right? Because like you see, calculate the time of contact with the ground station. You see that show the distance traveled in which it can. Yeah. Then I'll just keep on looking. Uh, Aiyo, that one cannot. I cannot. There's no such thing. It can be anything lah. No lah. I mean, I think more or less worry about the definitions that you always cannot remember. You get what I'm saying? Like let's say for example, I ask you, what's magnetic flux linkage? You know, or what does magnetic flux density mean? What's the definition of flux density? So those are the usual ones. Or even simple things like this. What's the definition of a magnetic field? Yeah, that kind of, I mean, yeah, lah. So it's more of a case of like, don't think about the ones that they usually ask because there's no way to predict. I guarantee you there's no way to predict. Right? I don't, yeah, there's no way. They could ask anything, right? Yeah. Definitions are just like, 3 marks are, so you have to spend some time on definitions before the final exams. Yeah. I would say something like this, like I'm just looking at it, right? Um, I would just out of 20 marks, I would just try to get around 8. I won't bother with this for too much. Yeah, 8 marks, 8 out of 20. Okay. No, I mean for this particular question, because I mean I'm looking at it already, and then I think the one thing that they are being annoying on, right, is that um they're talking about like how the the satellite can keep in communication with a certain point as the Earth rotates, right? So essentially, it's just about like the size of this communication field. The country will or the country the Earth will rotate, and it rotates past this point, then the satellite will lose contact with that point. You know what I mean? So the whole question, I think the first part of the question is based on the premise of whether you understand how this thing works, right? And that would have caused you to like kind of like if you don't understand the first part, you would have lost 5 marks. Yeah, like yeah, you would have lost 5 marks. Okay. Then you look at part C. Part C will talk about like give another reason why loss of altitude causes the orbital decay. So this will be under gravitation. So this is something that we've done before, right? How does the altitude? Then they ask you, space debris can be dangerous for LEO satellites because they can be traveling at very high speeds. Or maybe there's some information above, so you can go and look for it. One advantage of a satellite at when a low polar uh and then one advantage when the geostationary orbit is used. Probably like we know what's the usual advantage of geostationary satellite. So this is under G fields. So this mark here can get, something here can get, something here can get. Um, Determine the width of the area when the satellite action is transmitted at a distance of this. Probably this is just math. Then they say for satellite at a polar orbit, determine the maximum amount of time can. Oh, okay. So it'll be the same 3 marks here and 3 marks here. If you didn't understand what was going on, then you would have lost these 3 marks as well. These 6 marks as well. So like 11 marks gone, right? Yeah. Like 6 plus 5, right? 11 marks gone. And then they ask you like, move to higher orbit. How does this affect the signal strength? How does it affect the contact time? Oh no, these two should be able to get lah. You know? Yeah, so you should be able to get. So around 8 or 9, no? Yeah, 8 or 9. But if you have enough time, right, then yeah, allocate. Okay, so if you manage to do the front part, right, rather quickly, right? If you manage to do the front part rather quickly, then you would be able to have more time, okay? But then again, limit yourself to 30 minutes max for your data response. Beyond that, law of diminishing returns, I would rather use, if let's say you have 40 minutes left, okay, I would rather you spend 25 minutes on this and 15 minutes on checking your work. Yeah, yeah, I would rather you spend that. Or you be meticulous about how you do your questions here, right? Be meticulous how you do questions here and then leave 30 minutes for 20 minutes, 25 minutes for the DRQ, right? Yeah, so time management. Don't get stuck on something for too long. So the most dangerous part is always like, the front question, the first 1 or 2 questions, they make you completely stuck, right? Then like you don't know what's going on, right? So you gotta tell yourself, okay, you know what? I can't deal with this now. Let me just go on to the next one. Because, if you look at the second question, you realize, oh, this is familiar, right? We've done this before. Yeah. So this is like easier to do, right? And then you have this like ideal gas equations. So these are doable. Like do them, and then afterwards tell yourself, okay, you know what? After this question, I'm going to go back to question one. Then go back to question one and try again. And then if it still doesn't make sense to you, then go on to question four, right? Yeah. So you have to learn time management. You cannot get stuck on something for too long. That's the most dangerous thing. Yeah. I don't think you will. I don't think you will. Um, when you go for exam, do you use black or blue pen? Try to use blue. Um, but unless you feel very uncomfortable using blue. But it's just that when you use blue, it's easier to spot what you're writing because your handwriting and the font size is about the same. And I'm afraid that you might just glaze over it, right? When you're checking a word. Yeah, so like blue will be a bit more striking, you know? Yeah. So yeah. So all these things we've done before. And then this is a question now. This is one I did on Sunday. Right? This annoying one, where you have that circumference thing. So it was a very unfair question. I just ranted at it for a bit. Uh, but yeah, I mean, other than from that, actually the rest of the paper is okay. Like yeah. So yeah, all the best. Yeah. Let me know how it goes, and then I'll see you for your next one as when. Well, for that paper one, right? Paper three. Okay. On Thursday. Thursday morning. I'm seeing you on Thursday morning. No, wait. Oh, your paper three is on Thursday morning, so I'm seeing you on Wednesday. Shit. Okay. So I will try to reserve some time for you at night. Um, I'm supposing that some of the concepts that we've gone through so far covers a bit of paper three as well, but um, yeah, yeah, yeah. I'll okay. If you ask me questions later tonight or maybe tomorrow, I'll try to reply you by before 11:30 in the morning. I'll have my phone. I'll try to reply you, but if there's some things that I really cannot, then I hope you're okay with it. Right? Yeah, we'll settle it the next time around then. Okay, see ya.